Okay, welcome back for continue. So we continue our teaching. So welcome to the tutorial 8 in the mechanics of solids. So the mention is part for the transverse, shear stress and shear flow. So typically this question will be for the build up and also some that will be combined with the composite beams together to work out. But if the question itself is not that hard, but the main thing is how we can work out the problem from the two ways. First one, how we can work on the moment of inertia is for the whole structure. Second one is for the Q. So Q is very important for you to work out. So you must from the location of interest to the utmost. So you must know that's from the way to work out. Okay, let's see the first question here. If the applied shear force V is equal to 900 kilonewtons, determine the maximum shear stress in the member. So of course, we should know for the maximum one, David will be, as we see, that will be used for the flow. But remember, for the maximum one, definitely will be in the center of the part. So the center, not just the center, is for the neutral axis. So that means from here, the shear stress, we should know that work on the equation, the tau equal to VQ over RT for this equation. So this equation, of course, we will know from lecture part. We should know the meaning of the structure. The meaning, that means this one will be used for the structure, for this structure, for these things. The meaning of this, for each of the number, the V, was the V is from the most from the method of a section, we can work out. Q, that's the thing. So what's the Q? Q is the first moment of a rectangular area of width B and the height to somewhere. So that means from local location or initial location to the utmost. Now T, so also one from where, that's a T. So the location, width. So depends on where's the interest parts. Of course, we know that's why we use the equation to work out. But one thing we should know, where's the maximum? We see from the further back lectures, we know the maximum tau, I just write down for you, okay? The max, okay, tau occurs at the neutral axis. Clear? So we learn from previous lecture. Why? Because this one neutral axis will be large value, and all the surface will be 0. So like this way. So from here we can get this idea. We should find the neutral axis. Clear? So for this structure, of course, the neutral axis is quite easy for us to work out. Clear? As I mentioned, if you don't know how to use for neutral axis, sorry, you will fail this unit. 100% sure. Okay? Because neutral axis is a very, very fundamental. So that's why see this structure, we can draw this structure for the shear. You will see like this. Okay? For this structure. But we should write down all the parameters for here. You will see this structure here is a 25, 75, 25. So that means here will be equally write down this value. So 125 millimeter. Oops. Clear? 125 millimeters. Of course, we still can work out a little bit. So for this structure, come on, what's wrong? So then later on, come on. Clear? And then, of course, that will be 25. Okay? That will be totally 75. So neutral axis, so we can put something in the neutral axis, NA. Clear? So that means that we can say it's a Y bar. Pop. Clear? So of course we can do a lot of way to do the workout. So what's a Y bar is equal to, so summation of a Y bar A for summation of the A. So we did it so many times. Of course, based on this one, we can work out for the, let's say we divide this one by 3 parts. One part is for this. Clear? And one part for this, one part for this. Clear? We use this color or use other thing to do show you. So this part, this part. Clear? So that's why we can work out. For the first one, for the green color, so we can see that is 25. So that means half of 0.025. So meter times the area. So that means what, a 0.125 times 0.025. So all millimeter, okay? All meter here. Plus, because the same of this is 2 times the center, of course, that's easy, 0.025 plus half of this, half of this. So this one half of this, how much is 0.075 minus 0.025. So it's half of this things. So 75 minus 25. So I will not repeat this, give you details of these things. So this is the basic thing, okay? Of course, this parts times the area is a 0.25 times also half 0.075 minus 0.025 because of this and that total. So that's what from here. This value, okay, the minus. So I'll just show color to you. This is a Y bar. This is the area. Okay, so I'll show you for this. Divided by 0.125 times 0.025, okay, plus 0.025 times half of the 0.075 minus 0.025. This is from structure. So that's what we can work out is 0.029167 meter. That's for the Y bar from the top. Okay. So this is the basic thing. And work for the I is also, so because this one, so the structure is this structure. We know the structure here. So that's for the I, we should know how much of the I. So of course we should know, use a parallel axiom. Parallel axis theorem. We mention these things. So that means Rx is equal to IXC plus AD square. Clear? That's from the previous one. Okay, that's what from here we can work out the numbers. So how we can work out this thing? So we can easily to work out these parts because it's also the 3 parts for this kind of structure. So again, we can put these things as this structure of this. So of course we can still, I can use the color to show you because it's a little bit messy. I just put another one to show you. I just remove all the parts. So that means from here, the neutral axis somewhere, okay, for this. There's a neutral axis. Clear? So that means here is a point 0, 2, 5. The whole thing to here is a point 0, 2, 9, 1, 6, 7. The whole thing to here is a point 0, 75. Okay? So here is a point 0 to 5, something like this. So that's why from here we can get a neutral axis. So for the parts. So that means from here we can work out the parts yourself. So the R will be 1 over 12. From here we can see the cubic. Still with the cubic here. So rectangular here. So 1 over 12 times name B H cubic plus, because this one's IC, XC, but then a area 0.125 times area times the distance. So you see the distance here and this one, the distance. Okay, so that's what from here is 0.029167 minus 0.025 divided by 2. So that's the height. So remember, I show color again to show you the area. Okay, that is the distance. Okay, I'll show you another one. This one is RXC. RXC. So you should know this thing. Okay, I just keep reminding you. If you still don't know, you should do by yourself. Otherwise, we cannot teach anything later on. So with this only so many delayed. We give you too many details of this one. And also the T of this thing. So again, it's 1 over 12 times the B 0.025 H. H of course is 0.05 cubic. Okay, plus area. So 0.025 times 0.05. The distance again. Okay, the distance so will be equal to the area. So this one will be something like this. So that's what distance will be here. Distance. Okay, so that means 0.025 plus half 0.05 minus 0.029167. So that's what for here. Okay, square. Remember, there's a square for this one. Don't forget square. So that's what from here. This is the I. This is the A. This is D square. Okay, so of course the square will be here. Square. Okay, so from here we can get it. So that's why I get the number will equal to 2.6367 times 10 to negative 6 power meter per 4. So let's be from here, we can work out these things. So that's why from here we want to the neutral axis. So that means we from the center to any local. That's why I can see the color. I can change the color for this. Okay, I change the color to show here. So neutral axis. And then for the parts, we can show the parts here. You should this color to show you. Okay, but most for neutral axis. As well from here, neutral axis, that means we can use the K to use which way? You see, from the neutral axis to outermost. So the answer should be same. But remember, for this one, it's very hard to work out because this one is more complicated. But for the bottom one, it's quite easy because of two rectangular. Clear? Look here. This one, something structured like this way on the top. Clear? It's very hard to work out. But for the bottom one, only with a two rectangular. So that's why for here, we just let's say we can work out the Q max using the bottom two rectangular rectangular. Okay, so for easy working or calculation, because of two rectangular is quite easy to work out. So that means the Q max will equal to summation of YA. So equal to 2 times. So let's work from here is 0.075 minus 0.29167 divided by 2. Okay, that is the height times. So let's work from here. This one over here times. Okay, 0.025 times the height. Okay, this is the A. This is the area. Because two rectangular, okay? So as well from here, you can work out this answer. So of course, everyone know this one, we can work on tau max. So that's a VQ max over RT. So from here, we can work out. So we can get anything here. 19 kilonewtons times Q over I, we just work out 2.6367 times 10 to negative 6 meter power 4. So this is cubic, sorry. And times, remember the width is 1 here, 2, okay? 2 times 0.025. Remember this T. I use color to show you. Just wait a second, I use a T. I just use color to show you, okay? That's it. So let's work from here. We can work out 35.9 megapascal. Of course, you can also use work out the Qmax from the top segment, but that's more complicated. You still can work out. Okay, so you can do these things by yourself. So remember, this one we use a lot of existing knowledge. So if you are struggling, please practice all the lecture and the tutorial and the practical problems by yourself, because you must do this, get a skill. If you didn't do, you didn't get a skill. Trust me. You just follow this one because I follow some student this way. Yeah. I said this way. Yeah. I'm gonna say. Want to do the exam, I cannot do. I found many students like this way. Oh, no, basically, I understand what I should do, but I cannot do it. I said, you just say the solution. You seems you understand, but actually not. Okay, because when you do the problem, you will find where's the problem. Because really, I found many certificate students. I found many of these things. Okay, I just come back to the oh, please consider me. I know I can know how I can do, but I just cannot do it. I know how I can do, but I didn't do. So this is a very common issue. But I will say, sorry, university does not allow us to consider other things, only consider paperwork. So please, don't just say, you look the solution, yes, get it. As I always mentioned to you, do it, practice, you will get the answer, okay? So that's why for this thing, I highlight these things to let you know, that's some tricky place. You should know this tricky place. You should get this answer. Okay, hope you guys know this thing, because these things from engineering mechanics and will start from beginning to end. I say, when I talk to you, I say, start from that time, you didn't know, in the end, you cannot do the work. For the I, for the Q, for the neutral axis, for the three basic things. If you cannot do, then you cannot solve problem. Okay, that's a basic thing for you, please. Okay, we see another question. So this question was last year standard final exam question. This question. Okay, this real question in the last year. Okay, so just letting you know how we can solve problem. Okay, this is composite beam. So it's constructed from wood and reinforced with a steel strap. Calculate the maximum shear stress in the beam when it is subject to a shear of V equal to 50 kilonewton. Take Young's model of a steel, 200 gigapascal, and wood Young's model is 15 gigapascals. So if you look at the question itself, it's very similar to the last lecture for the composite beam. Okay, but this time because we're asking to work on the shear stress, so that's why just combine last lecture and this lecture. So in a lecture example, we just show single material, but in more and more common, we use composite beams. So that's why the question will combine together. So to use the question, as we mentioned, for the tau equal to VQ over RT. So this is only for single material, but this is the composite beam. So that's why we should transform the composite beam into single material beam. Everyone clear? This is very important for you to realize. That's why this question will combine composite beam and this question. So that's why for you, please understand. So I say we need the knowledge to work out. So of course, hopefully you can get an idea if this comes to the beam, transfer into single model beam. Easy for you. Okay, because I beam. Clear? This is I beam for you. Because the wood will most transfer the materials with a no Young's modulus into high Young's modulus because can save area, can save room, and save material. Clear? So that's why for us, we should know how to transform composite beam into single material beam. So that's why from here, we need. So from transform composite into single. Clear? That's what we'll do one more step for these things. But for last lecture, we mentioned to you, because these things will transform the different things. Okay? We transform the thing, we should consider the transformation factor. Okay? So hopefully you still understand. The N is equal to the material. So the Young's modulus, the material to be transformed into which material we use. So that's why from here, so we can see the N will be equal to, because it's wood, we want to transfer the wood into steel, can save room. So that's why for N is equal to the wood on the top, Young's modulus of wood divided by Young's modulus of steel. Hope you understand, yeah? N, the transformation factor, is equal to the Young's modulus of the material to be transformed. Divide the material to after transformation. So well, say it was from wood to steel. So that's what from here. So we get a 15 gigapascal over 200 gigapascal. So that's what we can get here is a 0.075. Clear? So that means afterwards we need to transform wood into steel. So that's why we should find the width of the material after transform. That's why we say B prime for the steel. Remember, B prime steel doesn't mean after transformation, but this is not real steel, it's for the wood. But after transformation, that's why we use B prime. So equal to NB wood. So N is 0.075. Wood, how much? 175, the width. So 175. Okay, but we should convert into meter. Okay, all convert into meter. So that means 0.175. So equal to how much? We can use calculator. Is 0.013125 meter. So that means we should draw the figure. How much will be? So you can see here, that means something like this. Not exactly, okay, just let you know for these things, okay? Like this. So this means this is 125 millimeter. So this is a 300. This is a 10. This is also 10. Okay, that's the main thing over here. After transformation, that's the value will be, so this value, okay, B prime. I just put it here. I don't want to put the numbers here. Clear? So of course, that's the beam for this structure. So of course, this I beam, the neutral axis will be in the halfway. So neutral axis. Clear? So that's what we work on the I, auto transformation. So this is easy. We do it a lot of times. So I will not repeat this again. Okay, just let it write down. So 1/12, okay, 0.175 cubic, 0.32 cubic. Okay, minus 1/12 times 0.175 minus 0.17125 H. So I will be 0.11 3648 times 10 to negative 3 meter power 4. So we can work on the I. So then, so asking you the maximum shear stress again. Maximum shear stress, we should know this one definitely will be use the neutral axis. Okay, so that's why from here you can work this thing because it's a neutral axis. So you can see that load will transform like this way. So there's one like this way. You can remember the lecture we mentioned these things. Okay, so this one I hope you understand how to work on the I. Okay, I is like some this block minus these things. That's why from this thing. So from here we can work out the Q max is equal to summation of y over bar or y bar a prime y prime. So of course based on this one. So with the neutral axis was see the color like this way. Clear? That's the parts. So from the center to outermost. So what I can see from here equal to this was 300. So it was half of this kind of structure. Okay. So that's why from here we can work out this structure will be. So y bar for this structure. So that's why from here we can work out this structure. So half of the 300. So that's why here, so 150. So that's why point 150. Okay, because half. This one is 150. Clear? So that's why from here times the area is a point 0.13125 times the height point 150 plus on the top is half of the top 0.010 plus 0.15. So that's the area. Times area times the height. Okay, so they can see the number is a 0.4189 times 10 to the negative third meter power. So you must work this thing. I still put a show color for you. This one is a Y. This one is a A. So you should work out, okay? This really is from very basic things for this. So of course, based on this one, we can work on the tall prime, max, steel. Okay, remember this is prime, this is not real steel, this one. So VQ max over IT. So that means for the tall max, for the wood, will be equal to NT prime, so max steel. So that means equal to NVQ max over RT. So we can put the number in. So NV is 50 kilonewton times Q, we just work out, divided by I, we just work out, times T. Q, how much of this one? That's the thickness will be here. Clear? So that's why the thickness, I just use color to show you, times 0.1 0.0125 meter. Okay, because for this color here. So now of course we'll see that's about 1.0 megapascal. But we still should double check if you are not quite sure, because this is not from the real material, this is from the wood. We check this one for the parts of this one for the boundary of this way. Okay, we still can check this one from the boundary, from this boundary, this one. Okay, you still can work out these parts to double check whether this is maximum or not maximum. Okay, that's why you will work on this way. That's what roughly 0.68 megapascal. Okay, that's why from this you can also double check. Everyone clear? You can double check, just use this one because the area will be different and the number will be different. So that's why for here, so please everyone double check for the numbers. So that's why for here, so everyone can see from these values, so will be different. So the 0.68 megapascal of this thing. But remember, I said this is last year standard final exam question. You see, that's the easy way for you to work out. So not that difficult. Even though the basic thing your data can work out. Yeah. So not that difficult. So it's about when you do final exam, please use some time to distinguish which was easy for you, which was hard to you. You start from the easy question first. Am I clear? So this is very, very important for you. Okay, we'll see the last question. This question was real question, was 2023 standard final exam question, this one. Okay, this is also real question. Just show you how we can use the problem to solve. Okay, we see the question here. The beam is constructed from two boards fastened together with 3 rows of nails. Look here, 3 rows. This is 3. Okay. So if the allowable shear for the wood is a tall allowable is a 1 megapascal, determine the maximum shear force V that can be applied to the beam. Also, find the maximum spacing S of the nails if each nail can resist 3.25 kilonewton in shear. For the first part, quite easy because find the maximum force. We know that quite easy. Just find the maximum shear stress. Yeah, you can get it. So most of the way on the neutral axis. That's the easy way for the first question. That's similar for the previous two tutorial question. For the third one, a little bit. So the second question was a little confusing. Maximum spacing S for this question. That's why for this thing you need time to think about, because this time is a little bit different from the lecture question or examples. So we see here, just give you 1 minute to think about. So it's better for the spacing. So what we should do? Because we have this. You can find how this thing will be happening. Okay, for the first question, quite easy. So we know we use this question, tau is equal to VQ over RT. We know that's the question from the previous two, same way. But for third question, looks hard, but not really. Just a little bit confusing yourself. Okay, well, I'll use the example to show you how we can solve this problem. Okay, for the first part, we use the maximum shear force, V. So that's more or less similar to the last two tutorial question. Yeah. So that's why we use the question tau is equal to VQ over RT. So that's why for this equation, we use the full calculation. So of course, based on this one, we can see the cross-section area. So something like this, one board, another board for these things. Okay, so there's a one board, there's a connection of this. So of course, this still is rectangular. So this is 40, 40 for this, and it's 150. I put this a little bit, okay. So from here, the neutral axis will be on to the center to board. Clear? So that's why from here, we can work out. So it's I, it's a rectangular one. So still remember, I just keep reminding you is BH. So this is x. So Rx will be equal to 1 over 12 BH cubic. So that's what, please don't forget it. So that means 1 over 12 B, so it's 115 millimeters, so that's 0.15 times, remember the height here is for the whole structure. So that means 0.0, I use color to show you, 8 cubic. Because this H will be 40 plus 40. Okay, so that's why from here we can work out. It's a 6.40 times 10 to negative 6 meter power 4. And the Q max, of course, Q max will be halfway of these things. So, okay, that's a Y bar A bar times. So the half of these things, it means this one will be on the top of this. Clear? So of course, this one we will see last position. So that's a Y bar will be a half of the 0.04 meter times the area, height. So that will be, we can work out. So as I said, tau max will equal to VQ max over RT. So that's why is equal to tau allowable. Okay, so that's why V we can manipulate this equation. Okay, so the V will be equal to tau allowable times RT over Q max. So we can use the work to 1 megapascal times I T. How much of a T here? Because the whole boat width. So that means 0.15 meter over Q max, we just work out 0.12 times 10 to negative 3 or third cubic meter. So that will be equal to 8 times 10 power 3 Newton. That means 80, sorry, is equal to 8 kilonewton. So that's the maximum we can do. So that's why it's just, we work on the equation we can work out. So the second part for the maximum spacing. So spacing, you will see based on this, F is equal to QS. Okay? So from here, we know that F is equal to QS. But because this was 3 of this, and it's still more confusing. So whether here is a 3 or here with a 3. So come on, this one, which one should it be? So, hey, this is 3, whether this one or whether this one. Which one should it be? Because there's a 3, each can sustain because resistant. So that means each they can put a QS. But this time they can resist 3 times of this one, but for the S will be different. That's why we should use 3 F is equal to QS. So don't confuse this question. Because this one, 3 put together on one row. Okay? So that means from here, just change it a little bit. Let me look on the screen. Because if this 1, 2, 3 put together, that means the Q should be 1/3 Q. Everyone clear? But because this one here, we can say the Q should be Q divided by 3. That means the 3 should go to another side. Everyone clear? So 3 together, so that means with the 3 should put on the other side. Everyone clear? This is very, very important, okay? Because this one based on this. If a 3, that means here we should divide by 3 for each of them. So that's why you put it on the other side of the 3. So that's why for easy understanding, how many will be there? Just put it here, how many come to here? Because each consistent, that means 3 should be times 3/4. That's S could be changed. Everyone clear? Okay, so if we know this thing, then our thing will be quite easy, okay? Because Q max will be equal to VQ max over R. So from previous one. So that means from here, we can say 3F is equal to VQ max over R times S, because the distance could be changed. So that's why S will be equal to 3F R over VQ max. So that's why from here, we can put the value in 3/4, 3.25 times 10 to the power third newtons. I, we work out before, so 6.40 times 10 to -6 power meter power 4 over V, so will tell you V, so we work on 8 kilonewton. So that's 8 times 10 third Newton times V max, we just work out 0.12 times 10 to the -3rd power meter cubic. So that's why we can work out this one will be 0.065 millimeter. So that's why you can see this one is a 65 millimeter. Clear? So that's why please don't confuse yourself here. If you understand here, no problem. Because for the calculation itself, actually quite simple. Okay? Okay, that's all. Thank you very much. So if we still provide some practical problem, you please practice. Thank you very much.